could write it as T1 over P2 over T2, and the reason why is because we're just doing proportions here, and so either one will work perfectly fine. Here's the amount of gas affecting the pressure. If I add in more particles inside this container, as shown in this picture, they're going to hit the inside wall of the container more often and causing it a higher pressure. And so the more number of particles, the pressure also increases. And so we have a direct proportionality again. So we have N1 over P1 equals N2 over P2, or it could be P1 over N1 equals P2 over N2, and either this or this works perfectly fine. So now let's talk about its combined gas law. So from this slide, we found that the volume and pressure are inversely proportional and the variables are side by side. So we have P1 times by V1 equals P2 times by V2. From this slide, we found that the temperature and pressure are directly proportional, meaning that they are one on top of the other. So over here, I have my P already up here, and so my T1 has to be down here, and my T2 has to be down here, because pressure and temperature are directly proportional to each other. From this slide, we found that the number of particles and pressure are again directly proportional to each other. They are one on top of the other. And so now, going back to the slide, we have pressure up here, and so my number of particles has to be down here. And so this is now my combined gas law. You could use this combined gas law, or you could also use P1 over T1 over T1 equals P2 V2 over T2. And so a lot of people, actually this is the official combined gas law, but we're going to use this because it has that moles factor here, which is also going to be useful. So this is actually the combined gas law, but please start using this to begin all your calculations for gas law problems. So here is my, so let's start with the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Here's my Boyle's law, and Boyle's law says my variables are P and V, but the temperature and number of particles is remaining constant. So over here, my N1 does equal N2, and my T2 does equal T1, or T1 does equal T2. And so over here, the N1, I'm dividing by the same number on both sides, which means that I can actually cancel those out. And because my T1 does equal T2, I'm dividing again by the same number, so I could actually take that out. And this is my Boyle's law. It's also on the right side corner, bottom right corner of your cruncher. Okay? Over here, here's my Charles law, and I know that my variables are T and V, and my pressure and number of particles to remain the same. So let's start out with this combined gas law once again. And my P1 equals P2, so I'm multiplying by the same number on both sides, so I can actually take that out. And then I am, and my N1 equals N2, so again I'm dividing it by the same number, so I can actually cancel that out. And so my Charles law is V1 over T1 equals V2 over T2, and this is your Charles law. which is also in the bottom right hand corner of your cruncher. Gay-Lussac's law. Actually, let's start with P1, V1, N1, T1, P2, V2, N1, N2, T2. My Gay-Lussac's law says that my volume and my number of particles are constant, so I can actually just cancel those out, cancel that out, and here is my Gay-Lussac's law formula. Okay. Likewise, with the Avogadro's principle, start out with the combined gas law. And here my my temperature and pressure are constant. So pressure is constant, temperature is constant, and my two variables that are changing is the number of particles with the volume. So here is my Avogadro's law. Okay, remember that these are all proportionalities, and so if I were to write them as just N1 over V1 equals N2 over V2, that would also just be the same thing. Okay, so here I am, in all of these cases, I am comparing situation 1 to a situation 2. In other words, going back to my Gay-Lussac's law, if pressure were to increase, so over here, if my pressure increases, my temperature again would increase. Versus in my Boyle's law, if my pressure increases, my volume will decrease. So I'm comparing before and after. Here is my before, and here is my after. Once again, this is my 1 series are before, and this 2 series are my after. However, let's say that I really don't want to compare the before and after. I just have one instant, and I want to know how much volume will be if I know the pressure, temperature, and the number of particles. Then I need a law that is not a formula that is comparing before and after. I just need one instance. But before I get into talking about the gas law, I want to just remind ourselves about our standard conditions. So we know that that STP stands for standard pressure and temperature, and that just means standard temperature 1 atm, or which is the same thing as 760 millimeters of Hg, which is also the same thing as 760 torr, which is the same thing as 101.3 kPa. For temperature, it is 0 degrees Celsius, which is the same thing as 273 Kelvin. Okay, but I also have to let you know that 1 mole of any gas, it could be 1 mole of CO2, it could be O2, neon gas, it could be argon gas, of any gas or a mixture of gas, even like a mixture of like fart gas. 1 mole of any gas, whether it be a mixture or pure, is going to take up 22.4 liters of volume at STP. So when the temperature is 0 degrees Celsius and the pressure is 1 atm, that 1 mole of any gas will take up 22.4 liters. Now, going back to ideal gas law, we know that our combined gas law is P1 times V1 over N1 times by T1, which is also equal to P2 V2 N2 T2, and we know that that equals this random constant. We know that the proportions are always going to be constant, and that constant is R, but we don't know what this R is yet, but let's calculate this R. So let's actually just take this equation of P times by V over N times by T equals R. So I know that at 1 atm and at 0 degrees Celsius, that 1 mole of gas is going to take up 22.4 liters. So now we have pressure, this is temperature, this is my number of moles, and this is my volume. So by plugging in these numbers, I can actually find out what R is. So here's my pressure, 1 atm, times by volume, which is 22.4 liters, over volume number of moles, which is 1 mole, and times by temperature, which is in Kelvin, is 273 Kelvin. Remember that we always do gas law temperature in Kelvin, and that is going to come out to be 0.08 to 1, and the units that I have left over are liters times by atm over mole K, and this equals R. However, I could use the pressure in atm or in kPa. So let's try that in kPa. We know that at standard condition, pressure is 101.3 kPa, and at standard temperature, we again have 0 degrees Celsius, which also equals to 273 K. That 1 mole takes up 22.4 liters. So here is my 101.3 kPa times by 22.4 liters over 1 mole equals or over 273 Kelvin, and that gets us to about 8.314 kPa times by liter over mole K. So this is again my R, and they equal one another other than the differences in the unit of atm to kilopascal. If you were to do the same thing, we know that 1 atm equals 101.3 kPa, which also equals 760 millimeters of Hg. And so 760 millimeters of Hg times by 22.4 liters over 1 mole over 273 K, and that gets us to 62.4 millimeters of Hg times by liter over mole K. And this is also my R. The only difference is a difference in the unit of your pressure. And if you take a look, I'm actually going to change my color of my ink because it's really hard to see through all this. This number and this number and this number you do not have to memorize because it's in your page 3 of your cruncher, and under physical constant 1, 2, 3, 4, 5, fifth constant down is your R. So please note that your R value is over there. Please note that you don't have to memorize this. You might end up memorizing this one and this number because you're going to use it so much. But please know that it is all in your cruncher. And I think I spelled my cruncher wrong here. But anyway, you guys know what I mean. So let's try solving some problems.